everyone. I hope you enjoyed lunch, because we'll continue now with the next presentation. We will find out that everything that happens in Windows 8 stays in Windows 8 with Marian and Moti, so let's give them a round of applause.
Thank you. Thanks for the introduction. Hello, everyone. I'm very happy to have you today at this presentation. We will be speaking about what happens in Windows 8, stays in Windows 8. More specifically, we will be talking about vulnerability research on Windows libraries. My name is Marian. I am a malware researcher. I do reverse engineering for a small startup in California named Intsafe.h Incorporated, and we try to do detection of APT attacks.
Okay, so my name is Moti. I'm also a security research, do some work for COSING, and I do some data reading sometimes.
We all have our hobbies. All right, our agenda for today are, well, what are vulnerabilities? What are software vulnerabilities? How can you use them? Why are they actually interesting to find? Why are they valuable? We're also going to give you an introduction about how to automate vulnerability search, because everything that's faster is like better for lazy people as we are. We're going to present you an approach on how to find software vulnerabilities, specifically with an example of Windows. We're going to be searching vulnerabilities in Windows libraries. We're going to present you with a solution of our approach. We're going to show you how we implemented our idea of finding vulnerabilities. We actually shortened our demo very much. So this talk today, I think it's only like 30 minutes. We won't have a demo today, but we're going to show you what we plan to do next with our approach. All right, introduction. What are software vulnerabilities? Most of you will have heard about exploits and how exploits are used in the wild, and how these are actually bad for the internet ecosystem, how they actually enable hackers to intrude systems, steal data, compromise money, and so forth. But to this whole threat detection industry, or to the whole defense side, there's an offensive side. More interestingly, there is a market dealing with these vulnerabilities, as they are actually used to generate revenue on the threat landscape. They are worth money. And that's the reason why a very vivid vulnerability market has emerged. And so there's people like us searching for software vulnerabilities. There's an interesting definition of a software vulnerability brought up by a guy named Norris on security. I'm kidding about that. It was Bruce Schneier coming up with that quote about how software mistakes enable hackers to intrude systems, and these system intrusions can be turned into revenue. So he says that the internet is full with vulnerabilities, with known vulnerabilities, and we're out there to search for the unknown vulnerabilities, for exploitable vulnerabilities, which actually can be used in turn to intrude systems and to generate that revenue I was talking about. Here's a picture of the guy coming up with that quote. You might recognize him. This is Bruce Schneier. I actually got this very interesting picture from a website selling T-shirts with Bruce Schneier quotes. I actually recommend you checking it out. I really like his quotes a lot. All right, software vulnerabilities. How would you find software vulnerabilities nowadays? So there's different approaches. Most of them are quite a lot of work, some of them are less work. All of them lead you to the intended target, to the vulnerability, but there's different knowledge sets needed to find these vulnerabilities. Like, for example, application penetration testing and fuzzing. You actually try to find the vulnerability by penetrating the binary or penetrating a website or whatever vulnerability you're after. Try to shoot input at these objects of interest. Try to trigger a breakdown of the application you're targeting, and try to find out the vulnerability which actually enabled the breakdown of the application. Another approach would be from inside out. So you dissect the system itself or dissect the binary itself through reverse engineering or through review of the code, and try to more or less statically analyze the target and find a vulnerability in there. Both approaches work. They are different in time intensity, which you need to actually find vulnerabilities, but all of them work. Anyway, there's other approaches. and people came up with that were actually too lazy to apply these techniques I just described. As, for example, you could just track software bugs to find existing bugs that were never fixed. You could track software bugs to attack systems which were never patched with a patch for the mentioned bugs. You could actually more easily bribe people who produce software to introduce bugs into the system. Or the approach that we were after, you could go after security patches. You could search for these patches in systems where they were applied and actually find the vulnerability, the underlying vulnerability in older versions of the same system. As you might know, there are several versions of Windows operating systems out there in the world. There's also really old versions of this operating system being still used. And these older versions of Windows are often more vulnerable to bugs which were fixed in a later version. And this is exactly the point where we try to hit. So today we're going to be talking about vulnerabilities which exist in Windows 8 and were fixed in a later version. You might have heard, like just recently, there was the beta version of Windows 10 released. I don't know how long ago. Anyway, we grabbed these binaries and compared them to Windows 8 binaries. Like we grabbed the libraries and the driver files of these systems and compared them and searched for software patches or applied security fixes and tried to find the spot in the older version of the library if we could find this missing patch in there. All right, bit more about vulnerabilities. Who's interested in finding them, or why would these people be interested in finding them? Well, most of us, of course, hackers for having fun. You can crash a system, you can own a system, you can have your entertainment with other people's system. You could also, as I mentioned, do criminal things with these kind of vulnerabilities, write exploits to own other people's systems, steal data, or hack their bank account, or whatever you're after. There's also other parties like software companies or governments who I heard are after vulnerabilities. I'm not sure if I heard correctly there. I see someone nodding in the audience. All right, and there's a fifth component like the media, which I like a lot. We're really happy if someone finds a vulnerability and finds a new exploit because they push out a lot of fuss on blogs and the news about anything they find. Anyway, whatever the media is talking about is mostly just the tip of the iceberg. On the entire vulnerability market, you have the different entities who are like really after all these vulnerabilities. So then you have hackers finding vulnerabilities, sending them to governments passing them on to the industry passing them on to criminals, and criminals passing them on to the media, and everyone happy because you can trade something. All right, about the cost of vulnerabilities today.
Okay, so I want to talk about what happened when someone have a 0 days or find a 0 days, what he can do with it. So in the past, people just basically report to the vendor and they got credit about it and everyone was happy. But now there is a little more options because having the 0 days, it's like having a power in your hands. So some people trying to get some money out of it. So if this is like a small list of like prices that you got a few years ago, but this is like a price you can get in a different market. If you go online and looking for someone that will buy your 0 days, you're not going to find the interesting people. We'll find some public company that's willing to give you 5, 10, 15K for your work, but sometimes it's worth much more than that. But usually the people that find the vulnerabilities, they don't have access to other places. So usually they just report it. Sometimes people actually know, and there's another reason they submit to this kind of companies, because they know that in theory it can be exploitable, but practically not likely. So these companies is willing to buy stuff even if it's not fully working exploit. But there is another market, that's the white market. There is the black market. This is an example of white market. They buy it from the developers, and they sell it to their client. So there is the black market. How does the black market actually work? So there is these people that want your stuff, but they don't want you to know that they want your stuff. And they don't want any connection with you whatsoever. They don't care about you. They just want your stuff. So there must be someone in the middle communicate with the buyer and communicate with the seller. The buyer trusts this guy. He's probably called broker. And the seller usually have to give trust to the broker. Why we do this trust? Because there is much more money involved. What he can get in the white market, he can get 10 times in the black market. So usually, the broker knows specific people, talk with them, see what they actually need, and go find the people that actually have it, and basically negotiate between the two. The seller and the buyer will never meet, no matter what. It's only the broker. And the broker usually takes 10%, 50% for his work. Such thing can cost, as example, an exploit for a browser can cost easily 150 to 200,000 USD. If you have a jailbreak for iPhone, you can get $1 million. Already happen if someone is involved. So there is a very high value, and the people that buy it have the money. The money is not an issue for them. And for the developer, which is usually not so founded as the buyer, will be happy to get this amount of money, with not ask question, where does it go? So what happened when you sell the stuff to the black market? Sometimes it's go and stay quiet for years. There is 0 days out there for 2 or 3 years. They bought it, no one knew about it. They use it targetedly. But sometimes it goes to some fishy people, and they like using it to hack internet and site. And basically, that's example of perfect. Some stuff go to some hands. It was Office 2007. It was bought by the black market, and they use it to hack website. Eventually, it was caught, and the 0 day died. That was a waste of a 0 day.
The other one, the clicker. Thank you. There we are. So, yeah, we were out to find vulnerabilities, whatever we plan to do with them. Why would people want to find vulnerabilities, which was covered? Why would we want to automate it? Because we're faster. Everything's faster. Governments can hack, whatever, sorry, I didn't say that. Software companies can fix their stuff faster, maybe. The hacker can break more, the criminal can make more money. What were we after? Well, we were actually lazy bastards. We didn't want to have all this work with reviewing code and trying to find buffer allocations in libraries and software fixes and trying to reverse patches. We didn't want all this, so we came up with an approach to automate our goal. So the idea that we had, which we implemented in software, was actually to find security functions. Windows operating system provides some libraries with functionality that help coders to actually implement secure code and to check input values which could cause software, or which could be software bugs and cause the software to crash. Here's a simple example of the Quartz library in Windows. We named it Windows A and Windows B because our solution actually doesn't care which version of Windows you fit on which side. So we put A and B. I actually thought about naming it Windows 1 and Windows 2, but people could be confused as there's no Windows 9 and Windows, no, sorry, Windows 9 doesn't exist. Anyway, with the different versions. Our approach is to look at 2 different libraries and see if we could find any of these secure functions in there. In the example that you see on the screen, hopefully, you can see on the right side the presumably patched version, where you can see here the call to ulongMult. This is a function which secures the multiplication of a value. This often happens when memory allocations are done in the software. And as you all know, when the amount of memory which is allocated is too big or too small, or whatever, that value for the allocation is corrupted, you could have a problem later on in the execution flow. So this function helps to securely multiply these 2 values and see that a certain threshold is not exceeded. Anyway, on the other side, you can see the old version of the library, where exactly this same security function is missing. So you see the idea which we have is actually pretty simple. We look at the libraries and we search for exactly these symbols. You might know searching for symbols in libraries or in code with debug functions is not that hard. So our approach was to decompile all the libraries which you could get from Windows and search for these functions. You're going to see about this a little bit later. Anyway, in the next step, as we figured out this could be a useful approach, we were comparing calls to these functions. This is the very same library, the Quartz lib, which we put into either Pro. We just counted the amount of a specific save function. So here we have the ulong add, which is a function to secure the addition of values, which could be used to allocate memory. We counted and we figured out there's like, in the older version of Windows which we had there, there's 46 appearances of this function, and in the older version there was like 44 appearances. So looking at this, we saw there's 2 calls in there, in the newer version to this exact save function, which were not present in the older version. So we figured out in the older version there has to be something missing. But this would still be a lot of work to look into all these libraries and count the functions by hand. So we tried to automate it. I told you there's save functions in Windows. There's actually 2 libraries, the Intsafe and the StringSafe library, which provide this functionality to a developer, provide these functions to a developer so he can use it to secure his code, which is about type conversions, which is about mathematical functions, as you just saw, the multiplication, the addition, which is about string allocations or buffer allocations for strings. And these kind of symbols that you find in these libraries are exactly what we were searching for. So we're creating signatures out of these files, simply taking the symbol name as a signature and searching for the signature in the library. Here you see some examples of save functions, which is all about additions and all the stuff you can do with strings and type conversions from short integer to whatever integer. These are all the symbols that we put into our database. Here you can see a lineup of the approach. So in the first step, we had the Windows library, which we're decompiling with either Pro and Hextrace. The decompiled version of the library would then be a text file, which you could simply parse into a database. We had all the hits of the symbols, which you would find in the library. These data sets that we had then from 2 different operating systems, we would just compare and diff out the difference in the counts of save functions. So if we would see in a library we have a different amount of calls to these save functions, we would go to this library and search for the spot where they were missing. All right, now if you get the idea, I'm going to talk about the solution and present you with this beautiful, beautiful graph, which I produced. I'm very proud of it, actually, especially of the coloring scheme. Anyway, you can see here the different steps which we implemented. You have, in the first place, the library conversion to Windows 7 and 8, or Windows 9 and 10, no, Windows 8 and 10, C files. I see it here is a Python tool which parses the text files, puts it into a database, and from the database we would get out the diffings. A little bit more in detail. We used IDA Pro. Yes, it's true, for using the tool, you need an IDA Pro license and a Hextrace license to actually be able to produce the C files. We came up with 2 executables which help you in decompiling the library, so there's no manual work involved. We're actually just pushing some buttons, and IDA Pro is like popping windows beautifully and producing a lot of C files. This could take a while, like performance is an issue in our tool, but we actually don't really care if the tool needs like a day or a week or whatever, because we don't have to do anything, we just let it work. And after the step, we end up with our valuable C files. Then we can run the Python tool, which we implemented, which parses the C files and searches for the security functions, and there puts them into a database, which ends up in this beautiful database scheme. You can see it's also very complicated in there. No, I'm kidding. Actually, the whole approach and the entire system is very simple. The script we have is very simple, and the output is very cool. So from this database, where we had like all the libraries and the functions inside of the library and the signatures which were found inside of this library, which end up in the hit table, we could take all the hit tables for the older Windows version, for Windows 8, and for the newer Windows version, and compare them if we found different function calls in there. So finally, we ended up with these beautiful outputs, also highly complex, where we saw the function name, where the call appeared, the name of the call, and which save function was involved. And in the end, we had these differences in there. So we were searching for a different function call count. In this case, it's like 2 and 4, so we knew that this security function was called 2 times more in the newer version, while in the older version, there were 2 of these calls missing. So we could search for a vulnerability there. All right, so much about the tool. The tool initially was text-based. We had like this beautiful configuration, a lot of different configuration files. Pretty boring. We have all these instructions for the tool. We can like go to the command line and automate it and script the entire approach. Here's more of the script instructions. And actually, I admit I don't really like scripting. I know this is hard in the security community where people are all about Unix systems and trying to script everything and liking command line. But working with the tool, I actually figured out I would like more to click around and have an easier handling. So we came up with a GUI. This special GUI was a long discussion, actually. In the beginning, it was really boring. It was all great. And I figured out if we have 5 different functionalities in the GUI, we could as well give it 5 different colors. So welcome to the future. With this tool, you can instrument the executables that we created for decompiling the libraries in IDA Pro. You can automate the parsing of the C files into the database. And you can also automate the output into the diffing files. So you just only have to look at the text output. All right, this is the future. And now we're going to show you some of our findings.
Okay, so first, there is, as you guys know, a lot of files in Windows, and if you diff them all, you get a lot of results. 99 of the results will be false positive. It's just like a code practice. So Microsoft add like secure function everywhere, but sometimes maybe you can find something interesting. And I want to show one example that I choose today, and I didn't yet finish to analyze it to full, but I decided to release it. It's possible it can be exploitable. And I want to explain why and why not. So, okay, what you guys see here is the code that belongs to the Samba server. It's called srv2.system. If you first Google these drivers, you can see that there was vulnerability in this file in the past. So it will be interesting to figure out what Microsoft patched with this Safe API version. So here we see at the Windows 10 and the Windows 8 version. I don't know if you guys can see the assembly so well, but let me see. How do you do the slide stuff? Okay, so you see in the Windows 10, there is a function called RTL unsigned long mult. So this function basically was added by Microsoft to prevent an integer overflow. And in Windows 7, we can see the same stuff, but without this Safe API. They do the same thing, but this one just do a check. If it's going to be integer overflow, do not continue forward and execute the code. This one, just not. Just take the value in REX, and you can say RECX plus 60 is basically possibility input that can come from the network. And it goes exactly to EAX, and then it multiplies by 24. Why 24? EAX multiplied by 2 plus EAX is 3. Do a shell by 3, which is multiplied by 8, so it multiplies by 24. So if you take a number, multiply by 24, you can overflow it and above it. So this check is missing. What did I do next? I wanted to check what's happened in Windows 7. I took this code, and the entire code is missing in Windows 7. So I know that this is addition in Windows 8. When we did a diff between Windows 8 to the Windows 7, we didn't find this code, because there was no such code in the Windows 7. But when I did with Windows 10 and 8, I figured out there was a patch. So now, as you can see in the end, there is allocation, kernel allocation, and this allocation is basically based on the calculation here. So it's possible that someone can basically integer overflow and crash the Samba server again. If you go again to figure out what is this code belong, so this is the call stack. As you can see, the last function, this depatch blob, is the code that we saw now. That's the code that basically Microsoft added a secure function. Who called this function? The guy above, read state. Who called this function? The one above, read state and resume. And who called this one? Basically SRV create file. And then SRV do execute and create read, And me should know, the people that know Samba know that there is a command to send, and basically based on the command, the server performs something. And there is just command, I think it's number 3. If you send it, it triggers the create file in the kernel of Windows. So now what the guys have to do is basically to send just request and see breakpoint on the multi API and figure out if this traffic can be controlled by the web. And if so, it can basically execute, or at least denial of servers, the Windows server. That was one example that it's possible or not possible, can happen. I did not yet check it yet, but I will continue analyzing it. So a little more about the SMB. As you can see here we see a table. This table is basically in the, you can see all the possibility operation that the Samba server can do. And the create one is SMB.com create, number 3. And you see it's supposed to be create file in the system, but basically, if you analyze it more, it's likely you may be able to trigger something there. So this is just a simple example about can be useful, this kind of diffing. Even if 99% of them are false positive, 1% is enough. Thank you. If you have any question, pleasure. Okay, this one's for you.
I have two. The first one is that tomorrow I will give a presentation as well, and I will zoom more on the price list. That was the one I'm referring to, the 0 days price list. That was from an interview with Grug a long time ago by the Forbes, and I don't totally agree with that kind of approach on pricing of 0 days, but I'll explain tomorrow.
That's an old one. That's a 5 years old price tag.
Yeah, but it's not about the pricing. It's about the methodology is really wrong. So I'll explain tomorrow. It's auto-promotion for my talk tomorrow. But going serious, why do you think that most of the hunters of 0 days are going for Microsoft and not like Solaris, HP, UX? I mean, everything is on Windows, and just a few are on other OS, like Unix, for example. What is your opinion? My opinion is that they just have access from a younger age to Windows systems, and that's how they develop the skills to Windows. So do you think there is kind of a lack in the community of reverse engineering and everything that you stated on platforms that are different ones? Yes. Okay, thank you.
I would also suppose, like, myself, I'm not an exploit writer, but I guess that the attack surface that Windows actually provides is way bigger. But it's a difference if, I guess, in the value of the exploit, how many people you can actually attack with it, right? So let's say you have an exploit for Windows 8, which might currently be the most widely used Windows platform, or the most widely used operating system at all. It's way more valuable than an exploit for an operating system which a small group of people uses.
The attack surface. Yeah.
Exactly.
Any other questions? No? Okay.
In terms of differences between 7 and 8, in terms of differences between 7 and 8, did you focus on all kinds of services or just particular ones? So the focus on diffing here is finding vulnerabilities in all libraries or specific ones?
Just drivers. Just drivers.
Oh. We did different runs. We tried on Windows 7 and Windows 8 before. There we did system libraries and drivers. And for Windows 8 and 10, so far we only did drivers, for the reason that, interestingly, in the driver files, we were way more successful in finding missing patches. That's just like theories on why it's this way. Maybe the system libraries or the userland libraries are better maintained or have been attacked a lot more before. But on the userland side, we were not that successful in our findings. Maybe security patches there are applied in more regular, I don't know. So in the second run on Windows 10, we concentrated on the drivers. And actually, the first thing that we analyzed was this hit. So the first thing we checked was a possibly exploitable vulnerability. So I guess in drivers, you're just more successful with this approach of diffing patches.
Okay, thank you very much for the presentation.
Thank you.